There you go. All right. We're in the second day of our second unit, statistics. Awesome. Okay, so here's our do now. We're making a scatter plot of this data. We have temperatures in Fahrenheit, and we have ice cream sales in dollars. So I made a little graph here, and to repeat what I didn't just say, your scatter plot or anything that you're showing information on visually, you need to have a title. So if you don't have a title on yours, I would like you to write temperature versus ice cream sales or something similar, just to show that those are the two variables we are comparing here. All right. Then we want to make sure that we have our x-axis and our y-axis labeled with the correct variables. So I went ahead and gave you those variables in the do now. Our temperature in Fahrenheit is going to be on our x-axis. So your scale might be different than mine, but what I did here is I made mine start at 60 degrees since 60 was the lowest temperature I saw. Now, I wanted to show you something today because yesterday I showed you how to make a break in a graph, but I showed you incorrectly, okay? I looked it up. This is how we do it. Plus, I think this looks kind of cool. So these little zigzags indicate what we call a break in the x-axis or the y-axis. Basically, all that is it tells us that we're skipping over the values between 0 and whatever the next value is. I did that only so that I wouldn't have to write 0 to 60 because those temperatures are not relevant to the data we're given. Yes?
I have seen graphs where they did a break that is two sets of looking lines.
Ooh, yes, I've seen that too. Where they do, I want to see if this is what you're talking about. I also saw something like this for the break where they do that. I'll accept however you want to do it. I kind of thought this looked cool. It looks like I'm like crinkling my line. So however you want to show that there's a break, it's just you cannot just put 0 degrees and $0 and then straight skip ahead to 60 or 200 and not indicate that there's a break there. So whether that's drawing this little zigzag, whether it's drawing slashes, whether it's, you know, making zigzaggy lines, I don't know, whatever you do, just make sure you're showing that there is a break there. We're missing temperatures here. So now we have our x values, our temperature 60, and I counted by 5s up to 95 degrees. The other thing that you need to have on your scatter plot or your graph is a label for the values on the x-axis. So we know that these degrees, we're not talking about maybe the degrees of an angle, or there's other things we could measure in degrees. I want to write that it's talking about temperature. So you want to put a little title down there too. Your graph's going to have 3 titles in all because your y-axis also needs to have a title. We need to know, what are these dollar amounts telling us? They're telling us about the ice cream sales. That's how much money they made. All right, so now we have everything labeled nicely, and we're going to plot our points. So on the day that it was 60 degrees outside, it looks like the ice cream sales were about $200, so I'm going to put a point right there. At 65 degrees, it was 220. So I counted by 50s here. So in between each one would be, this is 225, so I'll go a little below that. All right, yes?
We would have to leave that big of a space when we start the side numbers.
Do you mean like, would it be okay if your 200 was lower?
Yes.
That would be totally fine. It's just the only thing that is required is putting some sort of indicator that there's a break in your graph.
Okay.
So it doesn't matter if 200's all the way down here. as long as you put something in between 200 and 0 to show that it's not consistent right there. There is a broken part of the axis.
Okay.
Yeah, absolutely. Okay, now let's go to 70 degrees. Oh, no, I skipped one. 68. So that's going to be somewhere in between here. 65, 66, somewhere in here. And then they had $250 that day. So right there. Then we have 70 degrees and $280. Hi, Candy. Okay, thank you. I appreciate that. All right, so we are going to start at 70 and go up to 280-ish. So this would be 275 in between 250 and 300. So I'm going to put it a little above that. All right, our next degrees is 75 and $320 for that day. So about, there's 25, a little below. All right, next is 78, again, somewhere in between 75 and 80, and that's $350 for that day. So I'm gonna go to 350 here. All right, now I've got 85 degrees and $480. So I'm gonna follow this line up to 450, 475, about 480. Is that right? That seems like a big jump. We've got some interesting data here. From 80 to 85, yeah, big jump there. All right, next we have 90 degrees was $430, so up to 90, 430. There's 425, a little above. All right, and last but not least, 95 and 520. So up, up, up. There's 500, 525, a little below. About right there. All right, does everybody's scatter plot look a little bit like this so far? Good, yeah, give or take. It might not look exact, but it should be somewhat in the same, same area. Okay, so we have made a scatter plot. So first of all, the next part of our question says, well, not question, the directions. It says once we construct our scatter plot, done. Now we need to draw an estimated line of best fit. Now I'm going to tell you guys there is a formula that exists to use these points and calculate an exact line of best fit. We're not going to do that in here because it's just very complicated, and it's something that you probably won't ever use unless you are in a specialized field that involves predicting data. For the purposes of what we're doing, we're just going to estimate by laying down a ruler and looking at our points to see if we're about even on both sides. So what I might do to see that is maybe just count my points. I've got 1, 2, 3, 4, 5, 6 on this side of the ruler. 1, 2, 3 over here, so I probably need to move it a little. Let's see, 1, 2, 3, 4. I don't know, that's close enough. I'm not going to be able to get it exact. Is this about where you guys put it?
Yeah.
Close enough? Okay, let's draw a line. All right, here-ish. Close enough. There we go. Right about there. Looks pretty good. Okay, so there's our line of best fit for this set of information. So let's talk about what we can conclude from looking at this visually. We just plotted all the points that we were given about how much money is made in an ice cream shop and what temperature it was that day that they made that amount of money. So what do we notice about this information?
The higher it gets, the more people eat ice cream.
Yeah, guys, the hotter it gets, the more ice cream people seem to buy. And that makes sense. People like ice cream when it's hot outside. So, we're going to talk today about something that it's a word that we're going to use to describe this type of situation. We would say that since there seems to be a trend, since we can tell that as the temperature rises, the ice cream sales also rise, we would say that these variables, temperature and ice cream sales, have a positive correlation They have a positive correlation. They sure do. And we're going to talk about what that word correlation means. So just for now, I want you to know that that's what it's called, positive correlation. All right. Does anybody need more time to copy down what we've got up here on the board? Okay, we are, in that case, going to move on, and we're going to tell you guys what today's topics are, what we're going to talk about today. All right. Today, we are going to learn how to understand the difference between correlation, what we just talked about, and causation, something we'll learn about here in just a moment. Once we've talked about those topics and understood the difference, we're going to actually use what we did last unit, and we're going to learn how to write that equation for the line of best fit we found. And we can use that equation to predict data that we don't have. We're going to use it to write predictions. All right. So let's first talk about correlation versus causation. So I'm going to start with correlation. Correlation okay. So correlation is just a fancy word for the statistical relationship between two different variables. Basically, it means whenever one variable changes, the other variable tends to change in a consistent way. So whenever we drew this graph, we saw that as the temperature gets higher, so do the ice cream sales. These are correlated. They do tend to change in a consistent way. Now, there's two different types of correlation, and before we go into that, I'm going to write out a little definition for you in case you want to reference it later. So, correlation is the statistical relationship between two variables. And in parentheses here, I'll put that explanation again. It just means when one variable changes, the other tends to change in a consistent way. So when one variable changes, the other tends to change in a consistent way. little bigger for you guys. All right. There we go. So this is what correlation is. Now, there are two types of correlation. We could have a positive correlation, or we could have a negative correlation. So let's talk about the difference there. Positive correlation versus negative correlation. All right. Okay, so in a situation that two variables have a positive correlation, just like we had in our do now with the ice cream sales and the temperature, all a positive correlation is it's a relationship where as one variable increases, the other variable also increases. So I'll write that out under here as one variable increases, the other variable also increases. And I'll draw a little picture down here just to help, because sometimes whenever we're learning lots of definitions, I know when I was in school learning statistics specifically, there's a lot of terms we're learning, a lot of new content, and it can get jumbled in your brain pretty easily. So I think pictures can kind of help us remember. So a positive correlation is always going to look something like this. That line is going to be pointing upward, just like a positive slope would. Okay, next we have a negative correlation, and this is just the exact opposite of the positive correlation. So what that means is as one variable increases, the other variable will decrease. It will do the opposite. So let's write that too. As one variable increases, the other variable decreases. So there's the difference. And we'll draw a picture for that one too. So when we have a negative correlation, we're also going to have what looks like a bit of a negative slope. Our data points are going to point more downward. That's what our line of best fit is going to look like. So this is correlation. We have two different types. Correlation is just a way to refer to our data and analyze it. We can say once we graph data and look at how it presents itself, we'd be able to say whether it is correlated or not. if it's correlated, we're going to be able to draw a pretty simple line. While if it's not correlated, it might look like what we did yesterday when we plotted those hours studied versus quiz scores. This has no correlation here. We cannot draw any conclusions from this graph. There's not a lot of correlation. Now, if we got rid of some of the outliers in the data, like when somebody studied for 5 hours, they only got 50%, maybe we could clean this up a little bit and come up with a more accurate correlation. But in general, when we see a scatter plot or data points that are all over the place, you're not seeing much of a trend or a pattern, we would say that these are not correlated.
So that would be a negative?
This right here is negative correlation. Whenever you have, here, I'll draw some points. Yeah, so if it looks like what I just showed you here, let me pull it up again. This has no correlation. This has correlation. The dots are closer together.
Okay.
Yes.
So no correlation, negative correlation.
Yes, yes. So we could also draw a picture for no correlation. Let's do that. Let me pull this up a little. And I'm going to put some little points all over here so you guys can kind of see what I mean by that. So our data might be something like this, just for example. And over here, maybe our data looks something like that. All right. Now, off to the side, I will say data that has no correlation I want to make sure I describe this correctly. I want to say, does it sound right to you if I say data that has no correlation will not have an obvious line of best fit?
Yeah.
Let's say that. Okay. Data that has no correlation will not have an obvious line of best fit. And we'll draw a picture for that. So data without correlation might look something like this. It'll look more like that word you used to describe it yesterday, Erica. Our data is going to look nebulous, like a cloud. There's just no conclusions we can really draw from that. It's all over the place. All right, so here is our correlation notes. This is anything you'll ever need to know about correlation for this unit. Basically, when we look at our data, if the little points that we put are close together and they're all tending to point positively, as the x value goes up, the y, or as the x value goes up, the y value goes up, then we've got a positive correlation there. Yes?
So we're not going to be covering curves at all?
We're not going to be covering curves, is that what you said? Probably not in this unit, probably not. As much as I would love to. I wonder, I haven't gotten to look ahead much yet. Maybe that'll come in Algebra 2, who knows? So here's just a quick little label of our axes, because even I just mixed them up. All right. Okay, guys. So that's correlation. Now we need to talk about causation. So causation is not something that we can necessarily show visually. It's more of a reasoning. It's an idea, or something that we have to kind of conceptualize. So under this, I'm going to write it in red because it's important. Correlation does not mean causation, and I'll explain what that means. So this is a big takeaway that I want you guys to really understand by the end of today. Basically, causation, what that means is that one variable directly causes the other to change. So if we were to look at the data that we just plotted here, I have a positive correlation here between as the temperature rises, the ice cream sales get higher, we get more money. They are correlated. We can see that they have a relationship. As the temperature gets higher, so do the price, or so do the sales. But does that mean that temperature getting higher is the cause for making more money selling ice cream? Is the temperature rising causing people to buy more? Is it forcing them to? Is it directly making them buy ice cream? What do you think? No, it's not. So let's talk about that, because correlation versus causation is one of those topics that there's a little bit of gray area. It's a little tough to really pinpoint which one is which at certain times. And I will say, it is tempting to say that higher temperatures cause higher ice cream sales. And while there is a very, very strong, clear, positive correlation here, ice cream sales and temperature, they are related, but the temperature itself does not directly cause people to buy more ice cream. So there's other factors that play here, such as, I wrote some down here. People are more likely to buy ice cream when it's hotter, but you know, the temperature is not forcing them to buy ice cream. The increase is more influenced by behaviors and preferences. You know, I feel like traditions, moods, yes. So we only say that there is causation in a relationship if the change in one variable is the direct only reason that the other one is also increasing or decreasing. So let's talk about a bunch of examples of that, because I think that sometimes is the best way to explain something. And before we do that, let's write down what causation means. Here's my notes. Causation means that one variable directly causes it to change. It causes the other one to change. It's the reason. Okay, so let's write this.
You know what?
Uh-huh.
I have a question. So,
Yeah.
when I was pregnant with Latavius,
Mm-hmm.
and I would have to have my ice cream,
Yes.
like, if I didn't get my ice cream, like, my body went through some things. Like, my son was the cause of me having to get that ice cream.
Right.
Like,
There would be causation there. Absolutely.
All right.
For
I'm
sure.
in trouble.
That's funny. That is funny. Because, you know, that is a true biological reason,
Yes,
you know?
Yes, gosh, yes.
Pregnancy can do a lot of things to
Wow.
you. So here's that definition. Causation means that one variable directly causes the other to change. make sure that we have this a little separate. And like I said, we're gonna talk about a bunch of different examples because, like I've said before, statistics was something that it was really tough for me to grasp whenever I was in high school and in college. So I have always loved math because it's very black and white. There's a certain clear answer pretty much every time, or at least there's a set of answers. Statistics is a little gray. Statistics is more of a discussion topic. It's a thinking topic. You've got to reason about a lot of different things. And that's where I struggled. I like numbers. Thinking is a little hard for me. So let's go ahead and talk about those examples. I wrote a bunch of them down, and I'm looking for one of my pages. Hang on, I'm going to pause this while I find that page. Okay, so here we have some situations and some observations that people have made. People have collected data about these situations, and we need to decide, are these variables just correlated, or is there some causation there? Do these variables cause each other to change? So for number one, somebody decided to sample and survey children's shoe size and their reading abilities. So as a child's shoe size increases, we found that their reading ability also tends to increase. What do we think here? The question I would like us to ask is specifically is, does shoe size really affect reading ability? What do we think? No, guys. What do we think is the invisible variable there that's causing the change or causing the correlation?
Getting older.
Age. Probably age. As children grow, their shoes get bigger. As children get older, they probably learn how to read a little more. Right. So whenever we have two variables that are correlated, it doesn't necessarily mean that they cause each other to happen. It probably means that there is some invisible variable that we haven't considered, such as age. So we would say correlation I'm going to put a little check mark. It is a correlation. And then for causation, I'm going to put an X. And then we're going to explain why. So why is there no causation here?
Because it's not an actual cause.
What's not the cause, though? Let's explain it very specifically. Why do we know that there's not causation here? There are other variables. Can you guys tell me, I want to hear like a specific answer. Like for example, I would want to say this, you fill in the blank, does not cause this to happen. Chance?
Shoe size has nothing to do with their reading ability.
Yeah, shoe size levels out as at like a certain age. Despite that, knowledge still increases. And
Yes.
and people, I think a big shoe size usually have around college age.
Yeah, probably.
Sometimes even decrease.
Yeah.
7th grade.
Erica?
For plant growth and watering frequency, there are other factors that are considered for plant growth, such as exposure to sunlight.
Absolutely. Absolutely. There are other factors. That's what makes it a gray area. Let's make sure that we understand number one, then we're going to jump to number two. So I'm going to write for causation being no, that a child's shoe size does not directly affect. And when we say affect, I know there's an affect and an effect. Sometimes you spell it with an A, sometimes with an E. Quick English lesson. whenever you're using affect as a verb, meaning you're saying that it's affecting something, it's doing something, you use the A. So we would say shoe size does not directly affect. Now when you use it as a noun, like if you say here are the effects or the possible side effects, that's when it would be an E, effects. So your daily English lesson, not directly affect reading ability. Okay. So, another way that we can determine whether there's causation or not is if we say, okay, does that mean that, so we know shoe size increases, their reading ability also increases. If I were to decrease their shoe size, if that were possible, is that going to decrease their reading ability?
No.
No, it's not, because their shoes have nothing to do with their reading ability.
They should do it in China.
Yeah, the foot binding with like the teeny tiny shoes. I know it. Interesting traditions. Okay, let's look at number 2 now. Somebody was looking at plant growth and watering frequency. So they noticed that plants that are watered more frequently, they tend to grow taller and healthier. So there's a couple of questions that we should ask ourselves. One thing we could ask is, does watering a plant cause it to grow? If we stop watering a plant, is that going to also stop the growth? So what are we thinking?
That would be my answer, that water directly affects the plant's ability to grow.
It's not the only thing.
You are correct. So Erica did bring up a great point. Water is not the only thing that affects a plant's growth. Absolutely, it's not. There's also sunlight to take into consideration. There's also, some plants, when you water them more frequently, it's actually bad for them. This is where it becomes a gray area. It's circumstantial. So for number 2, we almost need a more specific set of data to analyze to conclude whether it's correlation or causation. So I'm going to give you guys a little bit of reassurance here. All I want from you in this unit is to be able to give your answer and explain it well, to back it up. Give me your reasoning. So you could say that there is causation here, because if I were to stop watering the plant or water it less, it does hinder its growth for most plants. If I water it more frequently, it might help it grow more. But it's not going to do that for every plant. Not every plant. What if I have a cactus? Or not a cactus, let's go with just a succulent. They only need water every 2 weeks or so. If I were to drown it in water every single day, I'm watering it more frequently, but you're going to kill it. So it's not going to work. So if you say that these are just correlated because it's not true in every case, not all plants that are watered tend to grow taller and healthier, you could argue that. But I'm going to say in general, the watering frequency, it will directly affect the growth of the plant. Whether if you water it too much, it'll make it grow more or less. The main question we're looking for here is, does this variable affect this variable directly?
Yes.
And it does. So in this case, I'm going to say that there is causation there, because the water, whether you're doing it more or less, it is going to affect the way the plant grows. But you could win me over if you argued me in a different way. So on your quiz eventually at the end of this unit, we will all probably have some variability in our answers. You guys might have different quiz answers depending on how you explain it to me. So,
Based on how the question is written.
yeah,
It doesn't say only.
right,
It says water does cause a plant to grow more, and that's what I'm.
right.
And you could also read it though,
where it says plants are watered more frequently.
Mhm.
So, and, you know, the more you give it water,
Right.
you know.
This would also depend on our definition of more frequently.
Right, it does. It depends on what does that mean, more frequently. Absolutely. There's so many things to consider.
If you're watering it every 5 seconds, pretty much any plant is going to die.
And if you're
Yes.
watering it every 5 seconds, you got a problem.
Absolutely.
So, you know, it might be an OCD issue, you know.
Now, we're going to say in this case there is some causation because the amount of watering you give to a plant, the amount of water you feed it, affects its growth, whether that be positively or negatively. It affects the growth. So, for my explanation here, I'm going to say the frequency at which a plant is watered will directly affect its growth.
Or you could have said the frequency at which the plant is watered could directly affect its growth.
Yeah.
Positively or negatively.
Yes, absolutely. If you want to go a step further and say
Yeah.
that the effects could be positive or negative, absolutely. I love that. I love that. That's just a even more, I don't know what the word is I'm looking for. Gives me more of an answer. More explained answer. All right. Okay. Let's look at number 3. Smoking and lung cancer. Smokers tend to have a higher incidence of lung cancer compared to non-smokers. So there is a correlation there.
Yep.
I would argue there is also causation because there's been found dozens of carcinogens in cigarettes.
Yes, absolutely, Erica. That's a great point to bring up. So remember,
We know
go
that
ahead.
there are dozens of carcinogenic compounds in cigarettes.
Yeah, absolutely. So what we really need to ask ourselves is, does smoking directly affect how often we see lung cancer in people? Does it affect it?
And also there's more lung cancer people that don't smoke that's getting it. And it's
Right.
also, you know, like kids now.
Yeah,
That,
yeah.
No.
Right,
But
and-
like a few years ago, there was a big, in the news, a
Mhm.
lot of like preteens before the vaping.
Yeah.
That were getting it, that were in a household before people smoked.
Right,
Remember
right,
hearing
right.
about those?
Uh-huh.
So, but he's right, it's not just that. I mean,
Right.
yeah,
And it's
we-
not. But for the purpose of what we are doing, we can acknowledge and be aware that there are other things that can contribute to lung cancer.
So it is directed.
Yes.
Question.
We're just asking if there is causation between just these two. We're not asking, is this the only thing that causes it? We're just seeing, does this cause it? And Chance, you've been waiting so patiently with your hand up. What were you going to say?
I was gonna say recently there's been a recent push about, smoking or lung cancer and firefighters because they have found that if their equipment is unwashed after a fire, they actually
Yeah.
increase the chance of getting lung cancer. And also there's the fact that in the 1950s, whenever the uranium industry was first popping up, they actually did a study to find how smoking affected minors, and they found a higher incidence of cancer
Yeah,
compared to other.
And-
there's my evidence suggesting that.
Right. And guys, those studies are one reason that statistics is so important, to be able to know how to properly collect data so that we can analyze it and use it in the real world to say, okay, here's what this thing causes and here's the evidence. We see that the kids that were exposed to smokers growing up, this percent of them get lung cancer, and the kids that didn't grow up with smoke, this percent of them. You know, we can really compare a lot of different things and figure out a lot about a lot of things. Statistics is important. So let's go ahead back to this question here, number 3. We want to know is this data, we already know all of these are correlated. There's a correlation here. They all change in a consistent way. We want to know, is there causation here? If I were to become a smoker, does that mean I'm going to have a higher chance of lung cancer? Or if I was a smoker and I removed smoking, is that going to lower the chance? Those are the questions we want to ask. So what do you guys think?
Yes.
Yes, absolutely. Smoking directly affects the incidence of lung cancer. It does. It's scientifically proven. So what should we write for our explanation here? What do you guys think?
Smoking increases your exposure to carcinogenic compounds.
Yeah, let's write that. Smoking increases exposure to carcinogenic, which that means cancer causing. I hope I'm spelling it right. Sweet. Carcinogenic compounds. And the one part I need you to have in your answer is something about how this directly affects that. So we would say smoking increases exposure to carcinogenic compounds, which will
Directly affect.
which will directly affect and affect with the A. Don't write effect. That's wrong. Directly affect the incidence of lung cancer. All right, here we go. Let you guys see that a little better. Okay. Number 4 is a really interesting one. Somebody decided to compare data between ice cream sales and drowning incidents. Why? I don't know. It turns out somebody was looking at different bar graphs, or I don't know what these would be, probably a histogram. We'll learn about those later. But they were looking at these 2 sets of data, and they saw that both of these data points were relatively low during most of the year. You know, January, February, March, April, May, it started to go up, and then June, July, August, there was a huge spike in ice cream sales and in drowning incidents. There's a correlation there, guys, but we want to know, is there causation?
No.
No. Why not?
There's more people are out, so there's more people around.
Right, there's an invisible variable there. The reason that there's more drowning in the summer is because people swim more in the summer. Reason there's more ice cream sales in the summer is because it's hot in the summer. And people like to get ice cream when it's hot. They like to get ice cream to cool down. They like to swim to cool down. Yes, Erica?
Say they both have a causative link with temperature.
Ooh, yes. So temperature, if I were to compare temperature to ice cream sales and drowning incidents to ice cream sales, I'm saying things backwards, or temperature to drowning incidents, they also have, there is sort of a correlation there, absolutely. Now, I would say, I'm trying to decide if that would still be causation, though, because does the temperature rising directly cause more drowning incidents?
That means people
Well,
are
That's
cool off.
tricky because.
It's tricky.
Yeah.
Cool off.
I mean, it does raise the water temperature. People want to go into the water more if it's less cold.
Right. So do you think it's the temperature making people drown, or is it that they're in the water more that makes them drown? Probably that. So it's like there's an invisible variable within the invisible. It's like Inception. I don't know. There's a lot to consider here. There's a lot.
I think I love statistics.
What'd you say?
I said they're both activities that people do to cool off.
Yeah, they are both activities people do to cool off. Chance?
If you probably measure how many people are outdoors during these months, I probably wouldn't be surprised if the percentage of the people who drown is still the same. It's just that there's a larger population now that's affected by it.
Probably.
Number of people who don't even know what
Right. I know it.
Statistically, people who go ice diving are more likely to drown.
Now that makes sense. That makes sense. If you go ice diving, it's probably a little easier to drown than in a swimming pool.
Hypothermia.
Uh-huh. Right, and then there's another hidden variable, the body temperature that you experience.
Like losing the place.
Right. What if you jump under there and your eyes are closed and you look up and you're under the ice and not under the hole you jumped in? Oh my goodness. Okay. All right, so let's look back at number 4. First of all, there is correlation here. All of these that I'm giving you have correlation. So I now want to know, is there causation?
No,
Why?
not correct.
No.
Why is there not causation between ice cream sales and drowning incidents?
Because, just because you're buying ice cream, you're not going to, it's not going to cause you to drown. It's just because you're.
Not correct, that is.
Yeah.
Right. So there's that word that we want to always use to kind of back up our reasoning. Just like in the first one, we said shoe size does not directly affect reading ability. We could say ice cream sales do not directly affect drowning incidents. We know that. A lot of this is reasoning and just thinking, if I sell less ice cream, does that mean I'm going to solve the drowning problem?
It's more of a
No.
common sense.
Yes. So for our explanation, I'm going to say ice cream sales do not directly affect, with an A, affect. I'm going to get on you guys if I see somebody write it with an E.
I'm gonna do it just for.
I'll knock points off your grade, girl.
No.
Okay. Does not directly affect the amount of drowning incidents. All right. So that's 4. Let's keep going. Oh, what time is it? Ooh, we've got, about 3 minutes. How about this, guys? We've got a little more that I want us to still talk about today. So I'm going to let you guys go to lunch. Come back at 12:30 and we will talk just a little bit more. Hopefully it won't be too long. I won't steal your day from you. But good job for the first half. I'll pause this recording and I'll see you guys back at 12:30. Okay, we are back from lunch and this is our next page of notes. I had more examples. You're welcome to peek at them and look at them, but we're not going to go through them just yet because I want us to have time to go to the next thing, which is going back to that line of best fit. So whenever we see that there is a correlation in data that we've plotted on a scatter plot, we can draw a line called that line of best fit. Whenever we have a line, just like we did in the previous unit, there's an equation that we can write for that line. Whenever we get that equation, we can then use it to make predictions about certain data points that don't necessarily exist in our scatter plot. So let's look back at our scatter plot. and see if maybe we can come up with a line. So we were looking at temperature rising and the sale in ice cream. Now again, I mentioned this earlier, whenever you're finding the equation of the best fit line, there is a long, complicated process that you can create the exact formula of the exact line of best fit. We aren't going to be doing that just for the purpose of what we're using it for. I am not worried about you coming up with an exact answer, and that means our equations might not be exactly the same. As long as they are relatively similar, meaning if I've got a positive correlation here, I'm probably going to have a positive slope. My m is going to be a positive number. Whenever I choose my y-intercept, the b, our numbers should be relatively similar, probably within 10 of each other. It would be strange if I got plus 10 as my intercept and somebody else got minus 45. That would be way off. So let's go through the process of doing that with this correlation. All right, let me get some colors out. So I went ahead and wrote some directions here for you. What we've been doing all along is following these 3 steps to write an equation, and you guys already know how to do that, which is great. We're not doing anything necessarily too new here. We always find our slope first, then we solve for our y-intercept, and then we're going to write the equation with those 2 variables. Yes?
I got a slope of approximately 10 over 1.
Approximately 10 over 1. Interesting. 9 over 8. So those are very different. How did you get 10 over 1?
So I have 2 points. One is 70 to 80. The other is 65 to 30.
Okay, so 70, let me use a color. 70 to 80. So about here. Yep, so we're going to use this one. And what's the other point you used?
65 to 30.
65 to 30. Yeah, those are 2 great points that we could use. So I'll label those. 70 is my x and 280. I didn't do the right one. It's this one. Whoops. 70 and 280. And this one was 65 to, what was this number? Can you tell me again, Erica?
Which one?
65.
Oh, yeah. That one is 65 to 30.
Okay, 230. 65 to 30. Okay, so can you walk me through what you did to find your slope?
280 minus 230 equals 50.
Ooh, is it, you did 280 minus 230? Okay, perfect. So y, we'll call that y2 then. Let me label first because I'm going to get myself lost. x2, y2, y1, x1. All right, so you did 280 minus 230, correct?
Yep.
All right, and you got 50.
Yep.
All right, and then what did you do on the bottom for the x's?
70 minus 65
Okay, 70 minus 65.
equals 5. And then simplified it is 10 over 1.
Okay, so 70 minus 65. So that is going to be 5. Now, Erica, this would be an excellent method of finding the slope of, where's my ruler? Here it is. This would be an excellent method if we were finding the slope of this line right here. Because we found 2 points on that line. But if you notice,
All of our lines are going to be slightly different.
oh, very true. I didn't think about that because it is an estimate. It is an estimate. You're absolutely right. Okay, forget I said that. Maybe this is on your line. Okay, so we're just gonna go with that then. Your line might look a little different than mine. Maybe you made this point slightly lower. So we're gonna have some variability here. So then you said 50 divided by 5 was what?
It's 10 over 1.
10 over 1. Perfect. So you got a slope of 10. Okay. Wonderful. And then Michael, what did you do?
I just started from the lowest dot the line goes through and counted up to the highest dot the line goes
Okay, so this one and this one?
through. Yeah.
And did you said you just counted rise over run?
Yeah.
Yeah, you could do that too, guys. If you don't want to have to do the slope formula, you could also count your rise. Where does that one go? All the way up to here. Over your run, and you could simplify your points. Okay, what was your original rise, Michael? I'll see if it's close to mine.
I got 9 over 8.
Okay, you ended up with 9 over 8. Let me see what mine would be. This is about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 here, and each square represents $25. Okay, so here's the only issue with doing rise over run. It only works if our scale is the same.
Oh, yeah.
It only works if our scale is the same. So since each square for me represents $25, since I did 50 for 2 squares, that means I would have to do 25 times 12, because that's what I counted.
For me, all of my lines are 10.
See, that's smart. When you make your scales even, you don't have to do the extra math steps. So I ended up with 300 for my rise. And let's see, my run is by tens. Or let's see, from 5 to 70, 2.5, I guess. Yeah, so let me count this way. 5, 10, 15, 20, 25, 30. And look at that, Erica, I got the exact same slope as you. 300, nope, actually I got a different slope maybe. Let's see. No, I think it's the same. I'm not good at mental math, guys. Okay, 300 divided by 30. If I'm correct, it should come out to 10 over 1. 300 divided by 30. Yeah, we got the exact same slope. It's a lot more accurate than I thought it was going to be, guys. That's pretty cool. Okay, so we both got 10 over 1. And then, Michael, you said you got 9 over 8?
Yeah, like I scaled it differently than yours.
Okay. Does that mean, is your line tilted more this way?
No, it's tilted sort of, you know, not as
Mm.
not quite as steep as that, maybe.
Okay, so it's because of the scale. So in order to get an accurate slope for yours, we would need to figure out, you got 9 units over 8 units. You would need to see how many units each of your 8 is worth, and then how many units each of your 9 is worth, and make sure that you're multiplying to get the correct proportion.
Yeah.
Because the slope is really just, it's like a ratio. You know, we're seeing how big is this compared to this. And if I look, 300 should be much larger than 30. But it's not, because I squished these much closer together. This would be a much steeper line if I'm not wrong. Okay. So slope of 10. So if you did decide to look at that, that'd be interesting.
Mine was like that.
Yeah, see, that looks more accurate. That looks more accurate. Erica's line is much steeper. Okay, so we have a slope. I'm going to say, just because Erica and I got the same one, it was more consistent, we're going to use that one for our example. Is everybody okay with that? Okay, so we did step 1, find your slope. Now, if you want to be more accurate with your slope and you don't want to have to worry about changing your units and doing all this weird multiplying stuff, I would highly suggest just using the slope formula. Just plug in 2 coordinates that fall on your line. And then I know my M is 10. I need to find my B, and I'm trying to plug it into y equals mx plus b. All right, so I found my slope. How am I going to find my y-intercept?
Look at your graph and see where it lands.
You could look at your graph and see where it lands. How do we do it without a visual aid using our coordinates?
We rewrite this as an equation of the line.
Yes, we're going to try to rewrite it as an equation of the line. Which one of these do we want to use? Does it matter?
230.
It doesn't matter which one we use. It'll be the same answer. At least it should be if we do it accurately. So I heard Michael, you said let's do the 231. So let's do that. So remember, we've got a value for m that'll go here. So I'm going to write 10. I've now got a value for y, 230. So I'll put it here under my y equals. And I also have a value for x, 65, plus b. So now we're just solving for b. What would my first step be in this equation we've got set up here now?
First thing, we would multiply that out.
Yes, so 10 times 65, what is that?
650.
650. So I'll rewrite 230 equals 650 plus b. And now what?
Minus 650 on both sides.
Perfect. Minus 650 on both sides. So my 650s will cancel out. And what is 230 minus 650?
Negative 420.
Negative 420 equals b. Okay, we have our b. We have our m. We can write an equation now, just like we did before. What would my equation be?
Y equals 10x minus 420.
Yes, y equals 10x minus 420. So now that we've come up with an equation for this line, we can use it to estimate different data points that maybe we don't have the data for. We could estimate how much money they would make if it were possible for it to be 300 degrees outside. We would just have to know, well, first of all, it'd be $0 because we would all be dead. But if it were possible, maybe we could do a different one that would exist. How about when it's 32 degrees, when it's freezing? Yes, Erica.
It would be interesting to see.
Say what again?
It would be interesting to see at what point there's 0 sales.
Ooh. That's a great idea. So maybe we could figure out how cold does it have to get for our ice cream sales to be at $0. How would we do that? What do we think? We need to think about what our variables represent. We've got ice cream sales on the y-axis, and we've got temperature on the x-axis. So we want to know when ice cream sales are at $0, what our temperature will be. So what should we put into our equation to find that out? What do we think? Are we not sure? Okay, so let's think about it. Whenever I'm using my equation of my line to find a point on the graph, for example, I know from looking at my coordinates that whenever x is 65, Y is 230. So that means whenever I plug in 230 or 65 into my equation, so let's say I wanted to know what temperature it would be outside when we make $230. What I would do is put 230 for Y, and I would solve for X, and that would give me 65. Same thing with any of these points. If I want to know what temperature it is whenever we make $100, because the money is on my y-axis, I would plug in 100 for my y, and I would solve for x. It would give me the temperature, which is on the x-axis. So now let me ask you again, if I want to know how cold or hot does it need to be outside, what temperature does it need to be for us to make $0 in ice cream sales? So we want to know, we're gonna make $0, what is the temperature? How would I solve that?
0 equals 10x plus,
Oh, we got, yeah, minus 420. So absolutely, we could plug in 0 for y, because our y values are our sales, our money. So if we put in a dollar amount to our equation, we're going to solve for x, which is temperature. It will give us a temperature value. So let's try that. Let's put 0 for y. 0 equals 10x minus 420. And let's solve this. What would I do first?
Plus both sides.
Yep, we want to get rid of the 420, so plus 420 on both sides. And then I'm going to have 420 equals 10x. And what's my last step?
Divide.
Divide. I'll divide by 10 here. Cancel my 10s. What is 420 divided by 10?
420, or 42, sorry.
Yeah, x equals 42. So since we found out that x is 42 when y is 0, what do these numbers tell us about our graph? What is x and y standing for here, and how can we reason with this answer?
42 degrees Fahrenheit.
Yeah, this is going to be 42 degrees Fahrenheit. So this, our y, our ice cream sales, is 0. That means we will make $0 in sales when it's 42 degrees outside. That's our estimate. Does that mean that it will always be true? No, no.
Colder than that, I guess they're buying ice cream.
Right. right. So we can make educated guesses about information whenever we use that equation we found. We could make all sorts of estimations. Let's look at a different set of data where there's actually causation here. This is a correlation, but we can't draw conclusions because the temperature doesn't make people buy ice cream. It's their personal opinions and their wants, desires, their needs that make them want to buy ice cream. Temperature doesn't necessarily directly affect it. So I am going to give you a set of data right here. We're going to go with this. I'm going to make it little because I'm going to draw big. All right. I crumpled this paper on accident. I was trying to feed it into the printer and it ate it. So we're going to compare distance traveled versus fuel consumption. So we're going to do distance in miles, and our fuel, we're going to measure that in gallons. Okay. So first of all, which is going to be our x values? Which is going to be our y?
Miles is going to be the X.
Yes.
Y.
Yep, absolutely. We're going to call miles our x value. We're going to call fuel consumption our y value. All right. And I'm going to fill this chart out. So at 10 miles, we consumed 1.2 gallons. 20 miles, 2.4 gallons. 30 miles, 3.6 gallons. 40 miles, 4.8 gallons. 50 miles, 6 gallons. And 60 miles, it was 7.2 gallons. Okay. So we can actually notice a pattern here in this data if we think about it. Every time we travel 10 miles, our fuel consumption increases by about 1.2 gallons. So 1.2 plus 1.2 is 2.4. 2.4 plus 1.2 is 3.6. 3.6 plus 1.2 is 4.8. So this is actually going to give us a very neat, perfect line if we were to plot it on a scatter plot. For the purpose of this example, let's choose 2 of these points. Because remember, we can also write these as coordinates. We've got x's and y's. Do you guys have a preference for which 2 we use?
Say 50 and 6 because
Yeah, good.
Yeah, let's do that. This one just has 6.0. Good eye, that's a smart one to do. So I'm going to write that one out, 50 and 6. So 56, and I'll label my y and my x. And what's another coordinate we could use?
Let's do 10 and 1.2.
Yeah, 10 and 1.2, why not? 10, 1.2. So I'll call this my x2 for 50 because I would rather do 50 minus 10 and not get negative numbers. Now, if you labeled them the opposite way and made this your first coordinate and this your second, you'll get the same answer. You'll just have a negative divided by a negative that will cancel to a positive. All right, so I have all of this data in front of me. Now I want to write the equation of the line of best fit so that I can predict, for example, how much fuel will be consumed. I'm going to write a question for you. How much fuel will be consumed after traveling for 200 miles. So we are going to figure that out by writing an equation. What's my first step when I want to write an equation?
Let's find the slope.
Yeah, let's find the slope. I'll write that to the side. Step 1, find slope. M. Okay, so how can I find slope with these 2 points?
We can use the formula y2 minus y1 over x2 minus x1.
Perfect. We're going to use our slope formula. y2 minus y1 divided by x2 minus x1. So what numbers will I put on the top?
6 minus 1.2.
Perfect. 6 minus 1.2. What am I going to put on the bottom?
50 minus 10.
Good. 50 minus 10. Okay, guys, I want you to try to work that out. Tell me what you get when you get your slope. I'm going to do it too. Let's see.
I'm getting a slope of 0.12.
That's what I got. Perfect, perfect. So guys, once you've done that first step of subtracting your top and bottom numbers, you'll end up with something that looks like 4.8 over 40. Now, we do not ever mix decimals and fractions, ever. So that's when we would go ahead and put this in our calculator and divide, and we would want to just have a decimal answer. So our slope is 0.12. Yes?
We could get the same number just by taking 1.2 divided by 10.
Absolutely we could. We absolutely could. That's smart. 1.2 divided by 10, also 0.12. Did everybody get this number for their slope, or did anyone get something different? Okay. We found our slope then. What should we do next?
Let's figure out.
Find the B.
Yeah. We're going to
Solve for B.
find or solve for B. Okay, so how are we going to do that?
Let's write out the equation of a line.
Yeah, we're going to be using our equation of a line, which is y equals mx plus b. How do we use that equation?
By plugging in one of the coordinates.
Yeah, which coordinate should we use? Doesn't matter.
Let's do x1, y1.
Where, which one?
X1 and y1.
Oh, I was like, I didn't see a 1 and a 1 for x and y. I see now what you're saying. So 10 and 1.2. Okay.
I'm using the first one. You can't say it.
And you know what? You absolutely could use the first one, and we should get the same answer. So let's try that. I'm going to write it out, and I want you guys to do it on your own beside me, and we'll check and see if we get the same thing. So I'm just going to plug my numbers into my equation. And the y-intercept, the b that you come up with, there's a very particular reason why you should come up with that answer. We'll talk about it here in just a second once everyone's done. I'm still trying to get mine. That's what I thought. All right. Are you guys getting 0 for B?
Yep.
So let's reason with it. Our B represents our y-intercept. So that's where our line is crossing the y-axis. And whenever the line is hitting the y-axis, our x value is always 0, right? Does everyone remember that? Okay, so x is distance traveled. When we have traveled 0 miles, have we used any fuel?
Nope.
No. So we could reasonably say that when x is 0, y is also going to be 0 in this case. Yes?
Gas and diesel engines do use a very tiny amount of gas while
Ooh, I didn't realize that. So if we were going to get really technical, maybe we would have to calculate how much fuel is consumed while the vehicle is in idle mode or whatever. I love that. I love that. A lot of things to consider. Okay, so what should I do now?
Write your formula, write your equation.
Yeah, guys, we found our slope and our y-intercept. That's all we need to write an equation. So, I'm gonna write that third step here. Write the equation. What's our equation going to be?
Y equals 0.12x.
Y equals 0.12, so 0.12x. Don't write plus 0. It's irrelevant. It will not be simplified. So we know that in the formula 0 is RB. This is not simplified. We don't need a plus 0. Y equals 0.12x. That is our formula. That is our formula. Awesome. Okay, any questions about this one, this particular scenario? Yeah.
It's not specific to this one, but when we have y equals x, we just assume that the slope is 1.
Yes.
That different from b.
Mm-hmm. Absolutely. Or say that again?
When we have y equals x, we assume our slope is 1.
Yes, we do.
So why are we, what is the technical reason for why b is assumed to be 0?
For this one in particular, or just in general?
In general.
Do you mean y is b assumed to be 0 when the slope is 1?
No, y is, when 0 is our b,
Mm-hmm.
we don't write it. When the slope is 1, we don't write it.
Yes.
Why the difference?
So here's the difference. Here's the difference. Whenever we have a slope of 1, we are multiplying our slope 1 times our x value. All that an equation of a line is it's giving you a formula to plug coordinates into and to find more points on a graph. So if I am never going to be adding another number to the coordinate because of the y-intercept being a certain point, then we don't need to include it, because whenever I'm solving for new points on my graph, if I were to plug in, for example, the 200 miles, I would be doing 200 miles for x, and I'd put it in here. So I would know that y is the fuel consumption, 0.12 times 200, and that's just my answer. If I add 0 to it, it will not change the answer. So we don't need to include it. Now, the reason that we don't write the 1, first of all, you could write it. It is an option. But we don't, because if there is the equation y equals x, or even y equals x plus something, when we take 1 times our x value, it's the same thing as adding 0. It won't change the value. So it's irrelevant information. So it's not that we aren't including the slope. It's just that the slope doesn't change the x value versus the y value. Does that make sense?
Yeah.
Okay,
it just
good.
annoys me that the number
I know.
is
I know it. I know it. And you know, if you want to write 1 for your slope every time, that doesn't bother me. Fine with me. However, whenever you do write the equation, the plus 0, I just, I don't know. I feel like that is slightly more irrelevant than the 1x. Because,
Especially when you write big equations, like up on a board, when you suddenly got to do like 30, every little thing starts to get cluttered, doesn't it?
right. It sure does. A lot of different pieces to keep track of. Okay, man, you guys are very intelligent, giving me a lot to think about. Like I said, statistics has never been my strong suit, so I struggle sometimes to give good answers for all your great questions. So there may be a time that I have to say, you know, I'm going to look that up and try to give you a better answer later on. But for now, that's the best explanation that I'm capable of giving, I think, for now. Okay, guys. Whew, that was a lot today. That was a lot. Let's see. Let me look at our topics. All right. All we did now, we found our equation. Now I need to answer this question. How much fuel is going to be consumed after traveling 200 miles? Erica? 24 gallons. How'd you find that?
I didn't use the slope.
How did you find it? I bet I know.
So I took 1.2 times 200 divided by 10.
Oh, that is, yeah. Okay, you could totally do that. What'd you say, Jeremiah?
Said,
Go ahead.
wow, that was a good way to do it.
Right, that's really smart. And what's wonderful about math and statistics and all of these topics is there's lots of ways to do it. So, yeah, Erica, if you want to explain that again, go ahead.
So we're using 1.2 gallons for every 10 miles.
Mm-hmm.
And we're traveling 200 miles.
So really, you set up a proportion. 10 miles for 1.2 gallons is equal to, what was it? 200 miles for X gallons. So you did like a cross multiplication thing here, didn't you? 200 times 1.2 divided by 10 equals
Yes.
X.
Yes.
Beautiful.
Right. You could also look at it this way. I love that, Eric. I'm so glad you brought it up. So this is the pathway that we're taking. Ready? 200 times 1.2 equals 10 times X. And when we solve for X, we're doing 200 times 1.2, and we're dividing by 10. So here's why you can do that. Isn't that cool? And then you're going to find your answer, which is 24. I like that. That's really neat.
Couldn't you just do 0.12 times 200?
0.12 times 200.
That's what that equation down there is.
Gives you 24.
Yeah, it gives you 24. That's right. You can do
Yeah.
that.
Now you couldn't do 1.2 times 200 because that's for 10
I was doing
miles.
this equation.
But this, absolutely, because if you plug your X value, which is 200, into this equation, we're not adding anything after. All you would do is 1.2, so I'll say Y equals 0.12 times 200. And you're going to end up with Y equals 24. Or, wait a minute. X. Oh, sorry guys. I'm telling you wrong. You know what I mean though, okay? Oh man. That's embarrassing. Oh man.
That would be some horrible feeling.
Uh-huh. Pretty bad. All right, yeah, Chance.
Well, I was gonna say, in this instance, I think only if I don't know if they would apply it to every number after that.
Mhm.
But you can just, like, if it's just like these two zeros here, you can just take 12 times 2, get 24 out of that, because at the end of the day, you're just going to move the decimal point to the front of the 2 zeros.
Right. That's what's amazing about multiplying and dividing by 10. Anytime you, like if I did, I'll write it up here, 4.5, I'll give you a random number, times 10 equals, all you do is move it over one place, 45. For however many zeros are in the 10, so if I did it by 100, there'd be 2 zeros, so I'd move it 2 decimal places. And that'll work every time. Something else we could do is say, when I travel 20 miles, I use 2.4 gallons. So why don't we just add a 0, get to 200, move our decimal point, get to 24. That works too. Kind of cool. There's a lot of ways to get to our answer, guys. There's no one exact path. Statistics, man. Crazy stuff, guys. Crazy stuff. It's not black and white at all. Woo! Okay. How do we feel?
Good.
Pretty good? Oh, well, that's good to hear. I'll tell you what, I feel crazy. Statistics is, you guys are teaching me, I'll tell you that. I can reason with black and white concepts. I love math for its black and whiteness. I love exact answers. I really struggle with these. The reasoning part of my brain wants there to be one way to do it, but there's not. That's not the reality, you know? And so you guys are helping me grow my mind. And I love it. I love it. All right. How do we feel about moving to an exit ticket? Let's get out of here. Okay. I want to give you, actually, I don't want to use graphing paper. I want to use this. Day 23 exit ticket. This was page 7. Okay. Okay. So I'm going to give you some data. And I want you to do similar to what we did in the do now. I want you to construct a scatter plot of the data given. After you make the scatter plot, draw the line of best fit. At least your estimate of that line. It's not going to be exact. And then I want you to see what conclusions you can draw from this data. What are you able to assume given the information that we have put in front of us? So I want you to tell me about if there's just correlation there, or if there's also some causation to go along with it. Okay, so I know this is a little more steps than our exit tickets normally are, but I want to see what you guys have got going on here. Here is our data. Hours of exercise. I'm going to say daily, and weight lost weekly. So if you exercise for 0 hours a day, we're gonna lose 0 pounds in a week. Let's say you exercise 1 hour a day, and guys, I'm not a health person. I'm not gonna tell you this is accurate. It's just some data I found. This person lost 1 pound. Here, I'll write pounds in a week. When they exercised for 2 hours a day, they ended up losing 2 pounds that week. When they exercised for 3 hours a day, they ended up losing 3.5 pounds in a week. Then, whenever they did 4 hours, they lost 4.5 pounds. And at 5 hours, they lost 6 pounds. Okay. So, I want you to construct a graph, and I'll go ahead and remind you guys, we just need an X and a Y axis like this. We don't need to draw all 4 of the quadrants. And I'll go ahead and give you your X and Y. Now, I'm going to have you do this kind of on your own, but I'm also going to do it along with you, because whenever we do take a quiz over statistics, anytime you're analyzing data, the scatter plot will already be given to you. So I'm not going to expect you to be able to construct a perfect scatter plot. I really mostly want you to just be able to draw conclusions from that data. So I'm gonna, if you're wanting to make sure you're doing it right, you're welcome to peek up here as you're doing it. Although I trust you
Are we
guys.
supposed to do that little heartbeat sign at the bottom?
Heartbeat sign. Where?
Yeah, the little jiggy jaggy.
Oh, the zigzag. Only if there's a break in your graph. Meaning, let me find this one. For example, in this graph, we went straight from 0 to 200. And then we went straight from 0 to 60.
Okay.
This one actually starts at 0, so we don't need any breaks. That's a great question, though. All right, so 0. Okay, so here's the data that I ended up plotting on our scatter plot. So what I really want you to do is to draw the line of best fit. Tell me if there's correlation or causation. And I think that's all I'm going to have you do. I would have you make predictions, but I don't know if it's realistic to ask you how much weight a person might lose if they exercise more than 5 hours a day, because 5 is already very excessive. So we'll keep this realistic. I just want to know these two things. Draw the line and then tell me, is it just a correlation or is there actually causation? Does the amount of exercise you do directly affect your weight loss? All right, that is all. I'm gonna end this recording and post it on YouTube. There we go.